just kind of hit basis with a little bit of what we did yesterday, and then we're going to build off that a little bit more. The first thing I want to talk about, there's a question in your homework starts talking about, I think it's question 8, like chopsticks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So they ask you, like story problem wise, they say, what is the, excuse me, gosh, what is the, it's terrible. What is the size of the largest square dinner plate that you can lay a chopstick on diagonally? Okay? So basically what it means is, if I've got a chopstick that I'm going to place right there to right there, and I think they tell you the length of the chopstick. So let's just say, I think in the last class, it was 28. So if my chopstick is 28 centimeters, they want to know, well, how big does that plate have to be? Okay? So there's a couple things going on here. My hopes are that you realize, oh, well, we've been working on 45, 45, 90, so that must be a 45, 45, 90 set of triangles there. Or my real hope is that you remember that this is a square. Squares have 4 right angles, 4 congruent sides, right? So a square is a rhombus. And what we know about rhombuses is that diagonals bisect opposite angles. Meaning, if this is a right angle right here, that's got to be 45 degrees. Does that kind of make sense? Okay. So we get a 45, 45, 90 triangle here, whether you look at the top one or the bottom one. And yesterday, what we kind of walked through, hopefully demonstrating to you, was if we create I'm going to call it a template, every triangle that we ever come across has a 45-degree angle and a 90-degree angle. The sides are going to relate in that proportion to one another. Okay? So if I were to take that and make it and draw it so that it was congruent to the one on the plate, right? They match up, correct? Can you see that the end radical 2 matches to the 28, right? And because the triangles are congruent, and I forced that on them when I drew them, then by CPCTC, that distance there and that distance there are the same, right? If we can use that idea, that gets us back to like chapter 4, where we say, well, if those are congruent triangles, then n radical 2 has to equal 28. And now I can divide both sides by radical 2. And I get n is equal to 28 over radical 2. If you type that into Math Excel, I think some of you probably have recognized this, they're going to say, no, that's not the answer. It's equivalent to what we're looking for, but you've got to adjust the format. Okay? So remember, last couple of days we talked about rationalizing that. And by doing that, all you do is you take that denominator and you multiply the top and the bottom by that denominator. So we get 28 radical 2 over 2. And if you type that in, they're going to say, no, not what we're looking for. It's the right answer, the right value, but it's not the correct format. What can you do with that 28 and the 2 on the top and bottom here? The 28 over 2 turns into 14, right? So you get 14 root 2. And that's what n is, so that's the side length of the plate. Okay, that would, n is going to be, again, in this picture here, it's that segment. So when I put it back on top of the square, well, that's the side of the square. That's the dimension that they're looking for. Somebody will ask us that eventually, we do some of these questions, and I think I 20-some odd questions in the homework, and they're like, I did 2 or 3 of them, and I saw a pattern, and I just used that pattern over and over again. And that's fun. And I think what you'll find out is, let's say that we do this problem, let's take all the story problem context out, and let's, instead of thinking that 28, let's make it, give me a number, give me an even number, somebody. 14. Okay? If I say n radical 2 equals 14, am I still dividing by radical 2 to solve for n? So it's the same algebraic step as what we saw up here, right? And when I do that, when I rationalize, I'm going to get 14 radical 2 over 2 eventually. Well, what can I do with that 14 and 2? They cancel, right? They divide each other. It's 7 radical 2. So we had a situation where it was 28, and then the side length became 14 radical 2. Now we have a situation where it's 14, and the side length became 7 radical 2. What do you think it's going to be if I gave you a side length to be 100? Or sorry, not the diagonal to be 100. What do you think the side length is going to be? 50 radical 2. Okay, does everybody see the relationship between the 28 and the number out in front of the radical of 14 radical 2? They're half, right? Okay. Now, that's why I asked you for an even number, is because each time we do this, when we divide by radical 2 and then rationalize, we're actually multiplying by radical 2 over 2. So you're cutting something in half because of that over 2 amount. Okay? A denominator of 2.
That's only when they give us the hypotenuse.
Yes, so that's when they give you the hypotenuse. Okay? You can basically cut the hypotenuse in half and slap on a radical 2, and you've got then the leg distance. Okay? If they start you at the leg distance,
You just plug it into the hypotenuse.
yep, you just throw on the radical 2 with it, and that gives you the hypotenuse. Okay? So there are little shortcuts that you can do if you. My hope is that if you're going to use shortcuts, you understand why those shortcuts exist and what generates them, what allows them to operate. But you can do that, and it might save you a little bit of time. The only thing that happens then is, okay, well, what if this is an odd number? So if that's an odd number like 15, same thing happens. It's just I write it as 15 over 2, and I multiply by radical 2. Does that make sense? Okay. And that's really what, I had 28 over 2 and multiplied that by radical 2, but the 28 over 2 works well together. Okay. So in the last class, I forget what the number was. They said, well, if I write 15 radical 2 over 2, should I simplify that as 7.5 radical 2? And in the field of surds, okay, S-U-R-D, which is referring to radicals, just the math word we use for it, simplifying radicals, we don't want decimals out in front if we can avoid them. Okay? So 15 radical 2 over 2 is the simplified version that we're looking for. We like improper fractions. And here's the reason. We did this morning in my trig class, so kind of shed light on this a little bit for you guys, because you're going to see it at some point in your futures. If I wanted to square these, obviously I should square them and get the same result. Okay? Does anybody know what 15 squared is? I'll say it times 225. Okay? What's radical 2 squared? 2. What's 2 squared? 4. Those cancel, leaves me 225 over 2. Does that make sense? Now, if I ask you to square this as fast, okay, can we do that? You know what 7.5 times 7.5 in your head is? No, you have to do this, don't you? If I don't have technology, I got 5 times 5 is 25, carry the 2. 5 times 7, 35, add 2, so 37. Put my 0, 7 times 5, 35, carry my 3, 49, 52, add down, 5, 2, 1, 6, 5. I've got 2 decimal places, one coming from that, one coming from that, so I start over here, move to 56.25, right? Does that make sense? Okay. Which is what that number right there is, 225 divided by 4. However, just the algorithm of multiplying 7.5 times 7.5 together that you've learned in the 3rd grade, I've already maybe done 2 or 3, 4 problems in my homework while my neighbor, who is actually doing the multiplication like that, is still working on the first problem. Does that make sense? So the purpose of leaving things as improper fractions instead of converting them to decimals is because later on when we do further algebra, we're going to have to leave them as improper fractions, radicals, that kind of thing, because it makes the algebra easier. It makes the mental math quicker. And you're going to find out, because the question is like, well, why do I want to be efficient? Because eventually when we get to harder level mathematics, I'm not trying to scare you or anything, but there will be problems that, it might take you 15 minutes to do. Okay? Well, if it's going to take me 15 minutes to do, and that's using every process efficiently, if I wasn't using every process efficiently, that 15 minutes might take 2 hours. Does that kind of make sense? Now, will you see questions like that in a high school math class? Probably not until like a calculus or a stats class. But I've seen problems that take hours to complete. Let's see here. What do you guys know? We'll just kind of, my plan for the next couple days is to, we talked about 45, 90s yesterday. Today I'll talk about 30, 60, 90s. And then tomorrow, kind of talk about them both again together. All right? So it'll give you at least 3 days of discussion with these topics. And then there'll be things that continually show up throughout the rest of the course. So what my hope is that you guys eventually realize is that right now we're working with just triangles, but eventually we're going to talk about this shape. What's that shape? Anybody know? Cone, right? And I'm going to ask you to find surface area and volumes of that cone, but when I do that, we're going to need essentially that little triangle that is on the inside of this cone to do that. Well, what I'm going to tell you is that that angle is 30 degrees and that's a right angle. And I'll give you this distance here to be 5. And if I want to find the volume of that cone, okay, I'm going to need this H. Well, there's a 30, 60, 90 triangle, which is exactly what we're going to talk about today. And that H then is going to be 5 radical 3. I know that distance right away. Does that make sense? So as we learn it now, but it's going to be a component for a lot of other questions throughout the year. So we want to make sure that we have a good grasp of this stuff. Because this process here alone is difficult. If I got to get to that point and then try to figure out how to do special right triangles again, it just compounds that difficulty. So I'll make sure we understand it first. Let's start with this triangle, and I'm going to put that distance as 2n, that distance as 2n, and that distance as 2n. So those are the 3 side lengths. So if I do that, what kind of triangle is that based on those measurements? If they're all the same. Equilateral, right? Okay. Now, n could be anything. It could be 1, it could be 100, it could be pi, or whatever. Okay. But each one of those side lengths is going to be the same. So that is an equilateral triangle. If it's equilateral, what was another feature about it that we're able to identify? Equilateral triangles are also equiangular. So if it's equiangular, what is each angle measurement here? 60. So that's 60, that's 60, and this up here is 60. Okay. Now, if it's equilateral, by definition, is also isosceles. So I'm just going to look at this as being an isosceles for this next step. Okay. If that's an isosceles triangle with those segments being congruent, this angle right here was referred to as the vertex angle. You guys remember that if I bisect the vertex angle in an isosceles triangle, it creates that segment right there. That is the bisector of that 60 degrees. If it's the bisector of 60 degrees, what does that turn that 60 into? 30 and 30. Okay? The reason I want to look at this as being an isosceles triangle is because if it's a bisector of the vertex angle, we had a corollary that said it also does what to the base down here at the bottom. Okay, it's perpendicular to the base, and that's key because now I have 30, 60, 90 triangles, right? But it also does what to the base? Which will look like, and up here it's to scale up there, so what does it look like it's doing to the length of that base? Cuts it in half, right? Does that make sense to everybody? So what I'm going to do, so if that base is 2n, I'm just going to remove so clutter doesn't become an issue here. We got this right angle there. If the base was 2n and we just cut it in half, we just got n, right? Okay. And that creates our 30, 60, 90 triangle. Okay. And it gives us two sides of a 30, 60, 90. So right now, if you know what the hypotenuse is, let's say I give you the hypotenuse to be 8. What would n be? It'd be 4, right? If this equaled 8, to solve for n, you divide both sides by 2, right? You can get 4. Okay. If n was 12, wouldn't the hypotenuse be 24? Just double it. Okay. So that's a nice link between those two segments. However, we don't have a link right now between either of those segments and that segment B. So let's see if we can do this. What theorem links the legs of a right triangle to the hypotenuse of a right triangle? Does that link them? Okay, so I'm going to use these values. If I got n is one of my legs, so I'll say n squared. B is my other leg, so I'll go b squared. And C is my hypotenuse, which we've called 2n. So I'll square that. Left-hand side, there's nothing we can really do there with combining like terms or anything like that, no order of operations. On the right-hand side, can I rewrite that as 4n squared? 2n times 2n. Now do you have n squares on both sides? So let's subtract those n squareds, or that one n squared from both sides, and I get 3n squared. Now I take square root, right? So you get b, so it'd be root 3 times root n squared. Square root of n squared is just n. So now I get b, this side here, to be whatever n was, times radical 3. So if we go back through and we say, okay, well, n was 4, 2n was 8, this side here would be 4 radical 3. And now I'm able, based off of one dimension, one distance on that triangle, I'm able to find all three. And that's kind of the nice thing about 30, 60, 90s is that, and 45, 45, 90s, they are generated through the Pythagorean theorem. But if I'm going to use the Pythagorean theorem, I need two known distances, right? With these two sets of triangles and these relationships that are set up here, all I need is one distance. And I can essentially use the Pythagorean theorem with that one distance. We're going to use this structure here. So in a 30, 60, 90, and this is the way I remember, because you're gonna have to make sure that you pay attention to this in the problems that we do. The n is consistent in all of these segments, right? So let's just let n, I'll do this in red, let's let n be 1 real quick. This segment would be 2, this segment would be 1, this segment would be radical 3, right? Okay? Radical 3 is approximately 1.75-ish. Which one of those numbers is the biggest? 2. Does that make sense because it's across from the biggest angle? Which one of those three numbers is the smallest? 1. Does it make sense because it's across from the smallest angle? And then the root 3 one is across from 60. If you can remember that, remember you got to use n, 2n, and n radical 3. N is the smallest. Always got to be across from 30. 2n is the hypotenuse. Always got to be across from 90. And then that will tell you where n radical 3 is got to go. And you'll be able to manipulate these problems and work through these problems a little bit easier. All right, so right now I'm going to get a calculator. Get your calculator out. Get whatever you're going to use for a calculator real quick. I created this thing last period, and just to kind of prove my point to you, I don't know what these lengths are, and when I change it, I mean, obviously, if I did know what they were when I started, I certainly don't know what they are now. Does that make sense? Okay. So what I want to do, so this is a 30-degree angle right here at the base. Object properties, let's see here real quick. Style. If that's a 30-degree angle, and we also have, kind of put in a weird spot there, even weirder there. Dumb. All right, I can't get the B where I want it. But if that's a right angle there, is everybody okay with the right angle being right there too? That's a 30, 60, 90 triangle, correct? Is that triangle similar to that one? Do they abide by angle? Do they both have a 30-degree angle and they both have a 90-degree angle in it, right? So these sides, how we compare these sides, so if I compare A prime to B and A prime to C, whatever that ratio is, should be the same as A prime to B as A prime to C here. Does that make sense? Okay. So let's kind of do some quick division here for me. I'm going to take a distance here, and I don't know, there might be some rounding concerns. Let's see if that's a nice number real quick. Yeah, kind of an ugly number, but just do it. Okay, let's go with that number. Take that number right there, A prime C, which is 10.5705. And I want you to double it. Just multiply it by 2. Okay? Now, just to preface this, when I show you this with GeoGebra is using the rounded values, the way I get this to work. Basically, that 10.5705 that you're seeing, we're not confident in that 5. Does that make sense? Okay? So it could be a 5 or it could be a 6. I'm not sure. So when we double this on your calculator, and then I show you what it really is on GeoGebra, we might be off a thousandth place, okay, or a 10,000th place. But if you double it, you got 20-something, right? 21-something? Did you get that number right there, 21.1411? Or something close to that, okay? Take this number real quick and multiply it by radical 3. You get 18.308 in the ballpark of that. Okay? Now, I didn't know what those values were going to be, but I did know how you guys could generate them, right? Okay? And it's because it's a 30, 60, 90 triangle. It's because no matter what triangle I deal with, okay, that has a 30, 60, 90 set of measurements, if I take this side here and divide it by that side, what is 2n divided by 1n? What does that reduce to? So reduce to 2. Okay. So let's see if that happens here in GeoGebra. If I take A prime B and I divide it by, so that's 2, and I divide it by n, which would be the A, it's the side across from 30, which would be A prime C. It's showing that number right there, which is 2, right? Now, no matter what, now obviously as I change my triangle, that number and that number that was terrible. Those two numbers are changing as I manipulate my triangle, right? So the numerator and denominator of this fraction here are changing, but does the quotient change? No, and the reason the quotient doesn't change is because that triangle is similar to that one, which is similar to that one, similar to that one, right? Okay. If I were to take, so this is n, and this is with the n radical 3 side. So let's take B to C, which is n radical 3 side, and I want to divide it by A prime C, which was the n side. So if I were to just kind of do that algebra real quick by hand, if you were to take the n radical 3 side and divide it by the n side, doesn't that give you radical 3? If you type on your calculator what radical 3 is, it's that 1.7321 number. Okay? So now as I hover over this, it says that is BC, which is the side opposite 60, divided by A prime C, which is the side opposite 30, saying that the quotient of those, 20.894 divided by 12.0631, is radical 3. And it's radical 3 all the time, no matter what those lengths are. Okay, everyone? And that's all because of similarity. Okay? So when we do these problems and we, even though the lengths of each new problem are different, but we use really the same approach, is because even though in that triangle there, where maybe this is 12, it's the same relationship between that segment, and that segment, as if that segment was 112, or as if it was 3,112. Does that kind of make sense? Okay, so we can use this, that's hopefully demonstrating why this template process always works. Okay, so what I want to do is I want you to go through a series of questions here with you to get in the habit of modeling, I guess, for you what I found to be the most effective way for students to work these problems. And it's similar to how I introduced the 45-45-90 process. Okay. First thing I'm going to do is I'm going to take my triangle they gave me, and I'm going to try to just somehow generate a triangle that looks congruent to it. Okay. With a 45-45-90, because both angles were 45, both acute angles were 45, we kind of neglected sometimes, and I never write them, the angle measurements inside the template. Here, if you don't put your angle measurements up and match them, you're going to make a mistake with the sides. Okay? So I want to make sure that when I do this, that this angle right here is not my 60 degrees. Does that make sense? Because that doesn't match that 30 degrees. Okay? So it's always important to put in your angle measurements in your template. And if you just want to put one in, you can. I usually put both in. So in my template, across from 30, remember that's always my smallest side. So it's in. Across from 90 is always my largest side, and it's double that, so it's 2 in. And then across from 60 is in radical 3. Okay? My biggest suggestion to you when you're doing your homework, don't try to keep things straight in your head. Draw the pictures down. You draw these pictures down 15, 20, 40 times, okay, over the next couple of days, maybe you do it 100 times. Then you can start doing things in your head, and the template becomes just kind of ingrained, right? If you've never drawn this picture, when you're doing your homework questions, you're going to struggle, I think, deciding what you're supposed to do and finding these values. So then I'm going to take this, and I'm going to overlap them. So when I overlap them, there should be one spot that I'm able to create a relationship, one spot where I'm able to create an equation. And you see, hopefully here, that the n is landing on the 12, right? So because I drew these triangles to be congruent by CPCTC, if these triangles are congruent, those two distances are congruent, right? Or segments are congruent, so their distances are equal. So I can say n is 12. And that's the easiest version of these problems is when they give me n, because now what would 2n be? 24. And that's the hypotenuse, so that's 24. And then across from 60 would be 12 radical 3. You just multiply by radical 3, and you've got your 3 side lengths now for that triangle. Is that okay? They give you n, you double it, and you multiply by radical 3, and that gives you the corresponding distances. Okay? Now, that, like I said, that's the easiest route. They could give you this. They could give you the exact same information. I'm just going to, just to make things a little bit easier for myself, cut and paste. Maybe this triangle. Wow. Okay. So I've got my 30, 60, 90 here. When I overlap them, that's terrible. This program doesn't like allow, for some reason, cut and paste to work real well with things that I've written. So if I do that, okay, and I overlap these now, what's the relationship? What equation do you come up with here? You guys see a 2n is matching up to 22? So 2n equals 22. So I write that equation. This is one a little less trivial. I've got to do a little bit of work here. Divide both sides by 2. And n is 11, right? Well, n is across from 30 degrees, so that's 11. And then across from 60 is 11 radical 3. All right? So just kind of walking through, so that's one question that gave us the inside, one question that gave us the hypotenuse. Here's a question that gives us the radical 3 side. Okay? So when I match those up, hopefully you guys can see that there is going to land on that there, right? So there's my equation. N radical 3 equals 3 radical 3. So what's n going to be there? 3. It's a one-to-one equation. We call that a one-to-one kind of correspondence with our left-hand side and right-hand side. To make the right-hand side identical to the left-hand side, or the left-hand side identical to the right-hand side, the n value has to become a 3, right? If you want to divide both sides by radical 3, you can do that. But regardless, you get n to be 3. And now what would 2n be? 6. And now I've got those sides of my triangle. Okay. The hardest ones that we usually get are something like this. Let me carry this thing down. Okay. Even though, so when I overlap these, you guys see that the n radical 3 and the 5 match up, right? Okay. So the 5 is my n radical 3 side. But the radical 3 has already been kind of multiplied through with another factor to where it generated the 5. Okay? So it doesn't have to be like the last one where it's 1-to-1, where you see the radical 3 actually existing in the number. Okay? What we're going to do here through division is actually pull out what number radical 3 was multiplied by to get the 5. Okay? So if I put those over one another and relate them, I get n radical 3 is equal to 5, right? If I want to solve for n, this radical 3 is my coefficient. So I divide by radical 3. I come over here and divide by radical 3. So I get that. Now, playing our rules with radicals, we need to rationalize that. And I get that. That kind of makes sense? And that's my n value. That's across from 30. So that is the number that when you multiply it by radical 3, you get 5. Okay? Now, usually when we talk about factors of a number, we're usually talking about like the whole factors, right? The whole number of factors, right? Okay. So if I think about 5's prime, so we won't use that one. If I use 6, 6 has factors of 2 and 3, right? And those are usually the factors we talk about. However, 5 radical 3 over 3 and radical 3 as factors give me the product 5. Okay, so we can talk about factors not necessarily having to be whole numbers. Now, here's where people make kind of the biggest mistake, is going from n to 2n. Okay, if I have 5 radical 3 over 3, and I want to go to 2n, that means I have to multiply by 2, right? So what is that going to give me up top? If you think if I multiply by 2. Let's multiply this whole thing by 2. What do you think the top's going to turn into? Is 2 the same thing as 2 over 1? Is that a fraction times a fraction? Can I rewrite this as 2 times 5 times radical 3 over 1 times 3? These 2 and 5s work together real well through multiplication. It's going to be 10 radical 3 over 3. That makes sense? When people make a mistake with this, they'll take 5 root 3 over 3. They'll double the top, make it 10 radical 3, and they'll double the bottom, and then make it 6. But when I double the top and I double the bottom, what did I really multiply by? 2 over 2, right? What's 2 over 2? 1. So did I really, is 10 radical 3 over 6 any different than 5 radical 3 over 3? No. So you just, when you double it, these kind of radical fractions, you just double the numerator, double the 5 out in front. Okay. I asked the last class to do this question. See what you guys can. I'll give you about 6 minutes here, and see what you guys can come up with. You can talk to the people around you, bounce ideas off one another. See if you can find. I want you to find everything up there: A, B, X, Y, and C. Okay. Before you get into that, how many 30, 60, 90 triangles are up there? There's 3. Okay, all 3 of those are 30, 60, 90. My suggestion, and now I'm going to show this and demonstrate this with you, I would pull them apart. Okay, but you don't have to. But I think it's just easier if you redraw them as 3 separate triangles. And the A value, so you got to have something to start your stuff with. Up here in the direction it says A. This distance here is 10 root 3. So give that a go, and we'll come back in a couple minutes.